So today we are going to begin with the definition of the limit of a function. So let's explore the definition. Consider a function y equal to f of x. So suppose here I have a function and this function is y equal to f of x. The function shown here is y equal to f of x. So consider a function y equal to f of x, which is defined for all values near x equal to a. So if a is here, suppose this point on the x-axis is x equal to a, the value of x is a. So around this point, if you go to the function up like that, okay, if you go to the function up like that, you can see to the left of a, the function is well defined. To the right of a, the function is well defined. But here in the middle, at x equal to a, it is not defined. So it can be defined, or even if it is not defined, that's fine. That's why we say, consider a function y equal to f of x, which is defined for all values near x equal to a, except possibly at a. So at x equal to a, if it is defined, that is fine. Even if it is not defined, that's okay. So we consider a function like that. Now, when x approaches closer and closer to a, when I say x approaches closer and closer to a, that is along the x-axis, from the left side when we go closer and closer to a, or from the right side when we get closer and closer to a. From the left when we go closer and closer to a, and from the right when we get closer and closer to a, what happened to the value of the function? We are going to observe that. When x approaches closer and closer to a from this side, from the left, the function will increase like this and gets closer and closer to this value here. And the value of the function at that point is somewhere here. I don't know what is that. Let's say the value of the function, the y value is, suppose that is L. So when you get closer and closer to a, when x approaches to a, the function approaches to a value of L. Similarly, when x approaches to a from the right, the function value decreases. The function value decreases and gets closer and closer to this value, which is also L. So that is the meaning here. When x approaches closer and closer to a, the value of the function approaches closer and closer to L. Then we say that the limit of the function f of x as x approaches to L is x approaches to a is L, and written like this. So let's rewrite this one in little detail here. So what I'm trying to say is when x approaches to a from the left, meaning of that is when x approaches to a from the left, the value of the function approaches to L. That can be written as, let me write here, limit, this is how we write, limit as x approaches to a. And I'm saying x approaches to a from the left. When I say x approaches to a from the left, these are the values which are less than this a. So we write a with a little minus on the top. Okay, like this. When x approaches to a from the left, when you see that minus, for this function is equal to L. And we say that when you are calculating the limit from the left, this limit is called the left-hand limit. You can also note that in your note catcher. Left-hand limit, that is the name of that. Similarly, when x approaches to a from the right, the value of the function approaches to L. That can be written as limit as x approaches to a from the right. The values on the right of a are more than a, so we write a little plus up there. Of f of x is equal to, still the function approaches to L. When x approaches to a from the right, the function value approaches to L. And we say that this limit is the right-hand limit. This is the right-hand limit. This is right-hand limit. And if the left-hand limit and the right-hand limit are equal, if the values from the left and the value from the right, they approach to a same value here, then we say that the limit exists. So this implies limit exists. or we say limit as x approaches to a, simply x approaches to a of f of x exists. Because from both sides, from the left and from the right, the limiting values are equal. Then we say that limit as x approaches to a of f of x exists. Meaning of that is when we just write a, that is from both sides, we go to a same value. And we write like this. The result is written as the limit as x approaches to a of f of x is equal to L. So this is how we write. This is how we write. So we say that the limit as x approaches to a of f of x equal to L. Or in short, when we go to x, when we go to a, or when x approaches to a from the left and right, and the value of the function also approaches to a single value from both sides, then we say that the limit exists, and the value of the limit is equal to the value of the function over here, which is equal to L. So that is the fundamental definition of the limit of a function. Example, sketch the graph of the function f of x equal to x cubed minus 8 over 4 times x plus 2, and use it to evaluate the limit as x approaches to 2 of f of x. So what we are doing here is we want to sketch the graph of this function, and we are using that graph to find the limit of the function. So what I'm going to do is I'm going to show you how to sketch this graph using a calculator. Okay, let's go to y equal to, and I'm going to get the fraction bar instead of divide sign. So I'll do alpha and then y and enter. This way I'll get a fraction bar so that I can type in numerator and denominator. In the numerator, I have x cubed minus 8, and in the denominator, I have 4 times x plus 2. And then let's graph this. So that should be the graph of the function f of x equal to x cubed minus 8 over 4 times x plus 2. Let's write this down. Graph of f of x equal to x cubed minus 8 over 4 times x plus 2 is as shown here. This is the graph. So the function is, this is y equal to x cubed minus 8 over 4 times x plus 2. So we have the graph. We are using this graph to find the limit as x approaches to 2. So in order to find the limit when x approaches to 2 of f of x, we have to find the limit when x approaches to 2 from the left and also from the right. So now let's do this. Limit as x approaches to 2 from the left. The values on the left are smaller than 2, so negative 2 of the function. So this is my function. The graph is here. When x approaches to 2, so if you look at the graph, when x goes to 2, everybody, this time I want all of you to look at the screen. When x goes to 2 from this side, okay, over here, when x goes to 2 from this side, from the left, the graph is going up like this. The graph is going up. The value of the function over here, when x approaches to 2, the value of the function approaches to 0. So limit as x approaches to 2 from the left of the function is 0. This is equal to 0. And also, let's do it from the other side. And limit as x approaches to 2, x approaches to 2 from the right of the function. So when you approach closer and closer to 2 from the right, so look here again, when you approach closer and closer to x equal to 2 from the right, from this side, okay, from this side, you can see that the function decreases and gets closer and closer to the function value over here is 0. So from both sides, you can see that the value of the function approaches to 0 from both sides. When x approaches to 2 from the left or x approaches to 2 from the right, in both cases, the value of the function approaches to 0. Both are equal. Meaning of that is the limit exists and the limit is equal to 0. So limit as x approaches to 2 of f of x is equal to 0. One-sided limit. When we talk about the one-sided limit, we'll talk about the right-hand limit and left-hand limit. When we say right-hand limit, that is the limit when x approaches to a from the right. And when we say left-hand limit, that is the limit when x approaches to a from the left. And if these two limits are equal, the limit exists and the value of the limit is equal to L. Example, the graph below is the function f of x. So this is the graph of the function y equal to f of x. So this is the graph of the function y equal to f of x that is given to you. Now we have to answer these questions. Here we are calculating the limit. Okay, we are calculating the limit at -1. You can see limit as x approaches to -1 from the left, as x approaches to -1 from the right. And what is the limit when x approaches to -1? What is the value of the function at -1? So let's look at this function. The function given here is definitely a piecewise defined function, you can see. So x equal to -1 is here. This is this vertical line, you can see. This is x equal to -1. So if you want, you can even show that line here so that you know where is x equal to -1. So this vertical line is x equal to -1. Now in the first part, if you look at the first one, we have to find the limit. Okay, in part A, we have to find the limit as x approaches to -1 from the left. So here is -1 when x approaches to -1 from the left. When x approaches to -1 from the left. From the left side, when you get closer and closer to -1, where is our function? Our function is here. So function is increasing, you can see. Function is increasing and getting closer and closer to a y value of -2. So when x approaches to -1 from the left, the function approaches to -2. This is 0, so that is -1, this is -2. So that is -2. -2. That is A. Now look at B. In B, we have to find the limit as x approaches to -1 from the right. So this time, x approaches to -1. This is your -1, but from the right. X approaches to -1 from the right like this. X approaches to -1 from the right. And here is the function. When x approaches to -1, the function is increasing and getting closer and closer to that value. You can see the function is increasing, and getting closer and closer to this y value. If you want to look at this y value here, that is 1. So the right-hand limit is equal to 1. This is equal to 1. So now you can clearly see the left-hand limit and right-hand limit are not equal. That means the limit as x approaches to -1 of f of x does not exist. DNE, meaning does not exist, because from the left, the function approaches to -2. From the right, function approaches to +1. They approach to a different value. So the limit does not exist. But how about the value of the function at -1? What is the value of the function at -1? At -1, here is a hole, so there is no value. Come down here, there is a hole, there is no value. But when you go all the way up here, that is the value of the function at -1. So when f is -1, the value of the function is here, which corresponds to 3. So the value of the function is 3. So left-hand limit and right-hand limit are not equal. That's why limit does not exist. And the value of the function is up here at 3. Example, the graph below is the function f of x. So here is the graph of the function y equal to f of x. We have to find the following. The first one is the value of the function at 0. So we are reading the graph. Value of the function at 0. When x equal to 0, the value of the function is here, that is at 3. So that is equal to 3. Next we have limit as x approaches to 2 from the left. Here is 2, this is 2. When x approaches to 2 from the left, the graph is going like this from the left. You can see it approaches closer and closer to a value which corresponds to, so here when x approaches to 2 from the left, so for the point x equal to 2, this is the point on the graph. When you approach closer and closer to that point from the left, you can see that the value of the function corresponds to 2. So this is equal to 2. The left-hand limit at 2 is, from the left side, is 2, because when you approach x equal to 2 from this side, the function increases and gets closer and closer to 2. Next, here we have limit as x approaches to 9 from the right. So here is 9. Okay, this is x equal to 9. When you approach x equal to 9 from the right, the function is coming like this from the right hand side. The function is coming like that from the right hand side here, and it gets closer and closer to a value of 3. So this value must be 3. This is equal to 3. Okay. Now the next one, limit as x approaches to 2 of f of x. When we say limit as x approaches to 2, you can clearly see there is no plus or minus on the top. That is, we are looking from both sides. So at x equal to 2, from the left, it approaches to 2. From the right, from this side, when you get closer and closer to the graph, it also approaches to 2. So from both sides, it goes closer and closer to a y value of 2. That means this limit is equal to 2. Example, sketch the graph of the step function f of x equal to 4 minus 2x for x is less than or equal to 1, and square root of x minus 1 for x greater than 1. Using technology, you are graphing this function using technology, and use it to find the following limit if exists. So first thing we need to do is we need to sketch the graph of this function using technology. So I'm going to demonstrate how to do this in TI-84 calculator. So in order to sketch that graph, we go to y equal to, clear any functions if they are here. Now the first function we have in our piecewise function is 4 minus 2x. 4 minus 2x. Now there is a condition for this one. We have to draw 4 minus 2x for x less than or equal to 1. So in order to write the condition, we put a slash here. And in order to put that slash here, we use this division sign. So division sign is the slash. Then to write the condition, begin the parenthesis. That's where we are going to write our condition. Begin the parenthesis, and our condition is x is less than or equal to 1. So here is x. And in order to get less than or equal to, you press second and then math. If you press second and then math, you'll see the list of inequalities. I need less than or equal to, which is number 6. Less than or equal to 1. Then close the parenthesis. Then go to next line. And here you are going to type your second function, which is the square root. If you hit second and square, you'll get the square root. And inside the square root, you need x minus 1. X minus 1. Move your cursor outside the square root. Put a slash, that is a division sign. And begin a parenthesis to write a condition. Our condition is x is greater than 1. So x, type x. Then to get greater than, you type second and then math. And greater than is number 3. Greater than 1. And close the parenthesis. And after that, hit graph. And that is the graph of your piecewise function. Let me change the window setting a little bit so that it looks a little more clear. So window, if you look at my Y window, it's a little different. So let's change this to -10 up to 10. Scale by 1. And let me graph it again. Then it looks more clear. So that is the graph of the step function. So this is the graph that we obtained from the calculator. Now we are going to answer these questions referring to this graph here. So the first part says we have to find the limit as x approaches to, this is x approaches to 1 from the left. So this is x equal to 1. Here we have, when x approaches to 1, you can see when x approaches to 1 from the left, from this side, from the left, you can see that from the left, the graph is decreasing. From the left, the graph is decreasing. The graph is decreasing and getting closer and closer to this value. The y value over here is 2. So the limit as x approaches to 1 from the left is equal to 2. This is equal to 2. Let's write the value, equal to 2. In part B, we have to find the limit as x approaches to 1 from the right. Here is 1. When x approaches to 1 from the right, from this side, when x approaches to 1 from the right, as x approaches closer and closer to 1 here, the function is decreasing and getting closer and closer to this value. Function is decreasing and getting closer and closer to a value. The value over here is 0. So it is getting closer and closer to 0. So this is equal to 0. This is equal to 0. Now you can see that at x equal to 1, the left-hand limit is 2 and the right-hand limit is 0. So these two limits are not equal. That means the limit as x approaches to 1 of f of x does not exist. This does not exist. We write D and E for does not exist because the left-hand limit and right-hand limit are not the same.